All right, looks like we've got a really good group here. I'm going to go ahead and share my screen and we'll get started. Welcome everybody to the Washington Capital Area chapter of ICEAA, and in today's luncheon, we are going to be presenting using TRLs to predict the future of nuclear weapons. And our speakers today are Abby Schendt, Ray Vera, and Mike Metcalf. Abby is a lead analyst at Technomics, and she's been supporting the NNSA in cost estimating and data-driven decisions. She previously worked at Rand Corporation on acquisition policy, and she's a graduate of the University of Maryland at College Park with an MPS in Applied Economics and the Rose Holman Institute of Technology with a BS in Physics, Mathematics, and Economics. Ray Vera is a cost supervisor for the Office of Cost Estimating and Program Evaluation at the National Nuclear Security Administration. He previously worked at the Defense Contract Management Agency as an earned value management specialist and Bank of America as a bond market quantitative analyst. He has a BS in industrial engineering and ops research from Cal Berkeley and an MS in financial engineering from Claremont University. And our third speaker, Mike Metcalf, is a project manager at Technomics, supporting the DOE, the DOD, U.S. Army, DHS, and the NNSA in cost estimating and data-driven decisions. He previously worked at the Institute for Defense Analysis, and he's a graduate of Lehigh University with a BS in Integrated Business and Engineering and an MS in Industrial Engineering. Welcome, everybody. Okay.
All right, I think we're set up from our end. Everybody can hear us and see the slides, I hope. I'll take that as a yes, why not? So my name is Mike Metcalf. My colleagues Abby Schendt, Ray Vera, and I have worked on some innovative analysis for the NNSA, National Nuclear Security Administration, Office of Cost Estimating and Program Evaluation, also called CP. Ray Vera is our cost estimating supervisor. Abby and I are Technomic support for the CP office. Ray and I have been here basically since the inception of the office in 2015, and Abby's been around for a while as well. So the work we've done was to support early cost estimates, supporting the CP mission for independent cost estimates of large programs, including nuclear weapons programs. And I think we already did our intros. All right. Before we get into the details of what we did and how we used technology readiness levels in a non-traditional way, we want to discuss a little bit more about what technology readiness levels are, what they mean at large, and what they mean within the NNSA. We'll then talk about how we use them to actually infer schedule estimates, how we collected our data and the methodology for using that data, the results and the impact of that results, and what we hope to do in the future. So for those of you who are not familiar, a TRL, a technology readiness level, is really a systems engineering method and technique for assessing within a program or activity or technology, how mature is this? So there's a number of organizations that use them. There's a number of standard measurement criteria and techniques, but they all, generally speaking, define for a system, a component, a program, a material, a technology, how mature is it and how close is it to actually being implemented? It's a great way to understand when you're setting up a program, the risk associated with the program, the level of maturity that you're at, and help you actually make decisions about what technologies you might want to insert, what risks you might want to take in making sure that you're cutting edge. But it's really traditionally a program management systems engineering exercise. We are, again, using it non-traditionally, as we'll get into. It's also a good way to communicate to decision makers where your program is at and how it's progressing over time. So on your left, you'll see a standard TRL thermometer. You start from the bottom and work your way up. This is based on the GAO, Government Accountability Office thermometer, but a number of organizations have their own. The definitions might differ across organizations, but the general concept will be about the same. What typically happens is within an individual technology or program, you look at do a technology readiness assessment, a TRA, and say, where are we at? What have we completed? What have we done? And then as time goes on, you progress through these individual technology readiness levels from the bottom up to the top. Or you might choose to stop a candidate technology and insert something else that's more mature or more successful. So starting in the bottom, technology readiness levels 1, 2, and 3 are often just ideas or concepts or materials, not necessarily anything practical or physical associated with whatever you're looking at. As you mature up, you might get to TRL 4, where you need a physical, actual prototype. Maybe it doesn't work. Maybe you don't know if it works in the environments it's supposed to, but you have a physical item. As you move up from TRL 5 and 6, you're actually testing whatever it is in the environments it will be relevant to. So, is it able to deal with the environment? Is it able to operate with the system that it's supposed to do, at least in prototype or testing phases? As you move up to TRL 7 and 8, you're talking about this is actually demonstrated able to work in the system it's supposed to work in. It's complete. The system that's around it is going to work as well. And TRL 9 is the system has demonstrated it will work completely, and your component or subcomponent or assembly or whatever it is that you're looking at is actually doing what it's supposed to do. So again, this can be assessed at a whole system or program level or down to any level of technology or component. A lot of the work we're doing at the NNSA, we're doing at the component level. So individual components make up a whole system. The assessments are typically done at the component level, and that's pretty important for the work we're doing and the ability to get the data that we have to do the estimating we want to do. So one important caveat is technology readiness level is not an indicator of difficulty. It's a set of criteria for how mature your technology is, but it doesn't necessarily inform how hard it will be to make that into a final end product. So this theoretical example demonstrates a level of effort it takes for 3 technologies, technology A, B, and C, to mature from concept or idea at TRL 1 to actual physical working item in TRL 8. So technology A required a little bit less effort and a little bit less time to move into the prototype phase, TRL 4, and then rather quickly was able to be demonstrated in the environment. So it presumably took less time, potentially less money, to mature technology A from 1 to 8. Meanwhile, technology C had a higher degree of difficulty. Maybe it was more complex. Maybe it didn't initially meet the environments or criteria that it needed to do. And so more effort, more time, maybe more funding was required to move technology C from 1 to 8. So your starting technology is not necessarily indicative of how long it'll take, but the span of time it might take to go from a TRL 3 to 8 is indicative or informative about the scope or scale it might take to mature technologies. And we use that distinction and that range in a lot of our estimates going forward. So you'll hear more about that as time goes on. But again, just for clarification purposes, not an indicator of difficulty, not a measure of how hard things are or how much effort's left, but a good sign of those things. So now I'm going to pass to Ray, and he's going to talk more about how it applies specifically within the NNSA.
All right, so for the next few slides, I'll talk about a little bit about our organization, the background, our acquisition process, and how the TRLs fit in with that acquisition process. So we're from the NNSA, or National Nuclear Security Administration. It's a semi-autonomous organization within the Department of Energy. We're primarily involved with ensuring the safety and security of the nuclear stockpile. In addition to maintaining nuclear deterrence, we also are involved with nuclear non-proliferation, promoting nuclear security internationally, and also the nuclear reactor fuel for the Navy. For the weapons program specifically, NSA uses the TRLs to assess maturity of its individual components that make up a nuclear weapon, and are assessed during the technology readiness assessment, or TRA phase, and evaluated at each milestone of our acquisition process. In the nuclear security enterprise, the individual sites or management and operating contractors, the organizations they're called the M&Os. They are the ones that are responsible, and they make up they're responsible for actually doing the work in the NNSA, and they include the national laboratories. So that's, you have the Los Alamos National Laboratory, you have the Lawrence Livermore National Laboratory, and you also have Sandia National Laboratory. The M&Os are the ones that they conducted TRAs based on the requirements from our system engineering group programs, and they're also responsible for setting the requirements for progression of the technology readiness or technology maturation process. So the TRLs shown on this slide are aligned with the milestones in our acquisition to include the first prototype during phase 6.3 or the technology development phase. You have system testing and technology demonstration at phase 6.4. And then you also have a component and system first production unit or FPU at phase 6.5. So the first production unit or FPU is the first deliverable warhead. That is the culmination of all the development engineering efforts to include the technology maturation of the components and the entire system. Okay, so the phase 6X process, that's what we call our acquisition process of our nuclear modernization programs. This is synonymous or analogous to the DoD instruction 5000.02. So we start off in phase 6.2, where the program undergoes early design studies in order to identify the major scope and characteristics of the weapon system. And they also identify early cost schedule and technical risks in the program. So the goal of phase 6.2 or 6.2A is for component development of prototypes, signifying the achievement of TRL4. In phase 6.3, we start looking at benchtop testing and some environmental testing for a limited set of components, and this aligns with TRL5. For phase 6.4, this is the start of system level tests on both the benchtop and relevant environments. Here, the components will undergo the final integration testing, flight testing, also final environmental tests to ensure that the final weapon system meets the requirements to achieve TRL8. Additionally, we use the acquisition milestones as a cross-check for the projected dates forecasted in our TRL schedule analysis, which will go on in later slides. But during this time, we're also continuing to make improvements. It is important to note, though, that we do not have a baseline schedule until the start of phase 6.3. So we can't use more traditional scheduling analysis methods, such as critical path analysis prior to this. So instead, we rely on these early phases on our TRL schedule projections to forecast the program milestone dates. And just important to note that one of our primary functions of our office, so how do we come up with this analysis? What we do, so in statute, our office is in charge of collecting data on the nuclear security enterprise, primarily for conducting our independent cost estimates. Our schedule analysis originally was based off, we did sort of a task burn rate analysis, or how fast we were accomplishing work or task activities relative to a baseline plan. So our early analysis focused primarily on milestone performance. But as we collected more data over time, we found more information on TRL component-specific data. And we found this on multiple programs in our enterprise. And we started to consolidate this TRL information into a database. Initially, the goal of the TRL database was to be used for our cost risk analysis. However, we realized as we collected more data points, we were able to track the progression of the TRL maturation over time. And this led to more specific analysis on schedule forecasting for specific components in the system. And then furthermore, when we were working on a congressional report a couple years ago in a weapons program that was early in acquisition process, we didn't have a baseline schedule. It was still early in the development. We realized that we can use the TRL database as sort of a schedule analysis tool pending an updated integrated master schedule. So we use the database to estimate how long we expect the number of components to get to FPU. That's the general basis of it. And then also how it impacts the overall system first production unit. And as I mentioned in the previous slides, we then cross-check these dates with the alignment to high-level program milestones for reasonableness and validity. So now I'll hand it over to Abby, who will discuss more about the process behind it.
So as Ray mentioned, we found that we could use our TRL data that we'd collected at the component level to compile up to a higher level schedule. And this was advantageous to us because our programs are multi-billion-dollar programs that span over a decade. And so looking at we don't have a huge range of programs to really look at. And so external to TRLs, our only other option is really to look at Milestone, which doesn't allow us to have a scope adjusted schedule. So in order to collect this, we first had to figure out, well, where can we get TRL data in a meaningful way consistently? And so our database is actually built out from WDCRs, the weapon design cost reports, BCRs, baseline design cost reports, our cards, our cost analysis requirements document, and then the site schedules and our NNSA integrated master schedule. So we took all of this information to compile by quarter what the TRL level was for every component that had been assessed. And from there, we built the chart that you see on the left up here, where we said TRL 2 was achieved for the environmental sensor in quarter 22 of our database, where we set the start of when we started collecting data as quarter 1. So 22 quarters in, this environmental sensor on this program reached TRL level 2. And so we then took that and we said, okay, well, then we also know that that same sensor reached TRL level 3 in 24 quarters. So it took 2 quarters to go from 2 to 3. And so that's sort of the whole basis of the data that we generated. You'll also see a set of red numbers in here. And those red numbers are where we notice that there's a lot of gaps in our data. Some of this is because we collect data often on a yearly basis, or for like WDCRs, BCRs, it's a one-time report that's aligned to the milestone of the program. So we might only get 2 or 3 reports for the entire duration of a program. And so in between it, that program might jump several levels. And so we really didn't want to lose the data that we weren't seeing because of the frequency of collection. And so what we did was we just put in a average between each of those dates to evenly spread out how long it was achieved, to make sure that we want to know how long it takes for a component to get from 5 to 8. And so we made sure we weren't losing anything, and we compared this filled average to the unfilled data. The total of our database after we had collected from all these components without accounting for fills or anything like that is counts about 40,000 data points, added an extra 0 there, spans 10 years, crosses 4, now 5 programs, and over 400 components that we can track at some level. Next slide. So then taking that data that we generated from that previous chart, we generated a normal distribution, and we chose a normal distribution because we can add the individual level distributions here to look at how long does it take us to complete 20% of all components that are going from 1 to 8, 8 being our component FPU. And then how long does it take to get 80% of components there, and how long does it take to get to 95% of components? And we found that this chart was a great way to communicate to senior leadership the risk that's being driven in by these large programs that have hundreds of components span across multiple sites, and why our programs tend to span over a decade. Because when you have 100+ components, 5% going wrong, you're adding 2 years to your, we say go wrong, but that last 80 to 95% completion rate is driving in a 2-year schedule growth into our programs. So we applied this normal distribution. Our sample size for every level was 3 to 70. And so, but this is the core basis of our estimate. And then Are there any questions so far on this? Cool. So then the second chart we managed to generate was starting to compare the levels that each of the programs had been at each of the milestones. So this was a sample 6.3 milestone. And so we looked at, well, we have a warhead that's completed all of its process. Where was it? At this point, we had an in-progress warhead, and we had the new warhead that we were trying to compare it to. So how does the distribution of the technology compare so that we can visualize, are we a more mature program at this point or less mature? So some of the differences that might be driven in here that we have to account for is the fact that since that completed weapon went through its 6.3 milestone over 10 years ago, we've had new TRL policy. So the defense programs has released a TRL calculator that has driven in more rigor into the readiness assessment process. And so what we might be seeing is is that we're at the same maturity, but we have a better understanding of it because we have more requirements and more rigor in the process. Additionally, we might have an insertion of new technologies because perhaps the stage at which we expect to use or not use nuclear weapons. We all know that within the last year, we've had significant political changes within the nuclear weapons enterprise and the world at large, where all of a sudden nukes have been thrust back onto the world stage. And so all of this can be driving in new program requirements. It drives in new technology requirements that then drives in less mature technologies into our programs. So then from the slide 2 slides ago, we then said, well, that's great that we can say how long it takes to get from conceptually to get from TRL 2 to TRL 8, but how do we know where our milestones are going to be? How do we decide when is the first production unit? What is the cutoff? Like, do we say 80% is good enough? Do we say 50% is good enough? And a lot of that will depend upon the programs that you are working on, but specifically we decided that as we're working on nuclear weapons, we wanted to really have a 95% complete weapon. At that last 5%, we assume that you can substitute in potentially legacy technologies in order to make sure that to prevent the program from extending out too long, because at that point there's just not we might get into too much budget risk. And so we said, when 95% of components are complete, that's when we're going to FPU or consider that our first production unit for the warhead. And so then when we have 80% of all of our components at TRL level 8, that's when we're going to transition from production engineering into starting to produce that first production unit. And then on our going from development engineering to production engineering, we looked at 80% of components having hit TRL 6, which is when you're transitioning from testing individual components into system level testing and environmental testing for the system.
So as Ray and Abby alluded to, we use this analysis in particular for an early stage program. The program had not matured any of its data collection, any of its scheduling, any of its kind of tracking of the program. But what was mature was how they defined where are we at today with our technologies. They went through a technology readiness assessment. Everything that they were planning to do with this weapon or some of the alternative options, the option space that was still there was defined because this TRL process is kind of rigorous and beneficial early in the stage. So in the past, when we've maybe had to do really, really high level schedule assessments or schedule estimates because we just didn't have a lot of detail on this weapon, TRLs were a great way to get detailed, reliable information consistent across the different parts of the weapon. And so, we were able to look at 40 or 50 individual items within the weapon and figure out where the problems might be based on what's happened in history. So that was a great addition to our estimating capabilities, especially on the schedule side. When we've looked at other metrics that we've done in the past, a lot of the things that people look at, particularly that you can understand in the early stage, are based on not really firm deadlines or criteria. Oftentimes within the NNSA, programs will take liens, they'll take on additional risk and say, we know we haven't completed everything for this milestone, but we're going to move forward anyways so that the things are done can keep going and the other things can catch up. What that's demonstrated in the past, what's happened in the past is those haven't caught up. And so we can clearly demonstrate early in the program the risk of that. And when we're in the middle of the program at some of these middle milestones, like the 6.4 milestone saying we're going to enter production engineering, we can more clearly say, here's where the technologies are at, here's where we're behind, and here's what we're worried is going to happen because of that. And then finally, we're able to more clearly demonstrate the impact of outliers. As Abby said, we can't deliver 80% of a weapon. Nuclear weapons have a criteria required that the labs have to sign up on. They will always work when they need to. They will never go off when they're not supposed to. And the technology and testing required to confirm that is extensive. And so there's no block upgrades. There's no you can fix that later for the most part. The weapon has to be done when we deliver it from the NNSA to the DoD. So we're able to say, listen, outliers aren't unusual. They happen on every weapon. We can't deliver until that outlier is resolved. And here's the type of time it might take, the type of effort it might take to fix those outliers. And we can define that at various points in time that we never could before with kind of a reliable metric. That said, despite the fact that we have 40,000 data points and 400 components, there is a fair bit of limitation to the data that we have. As Abby alluded to, these programs, the development process lasts a decade. The production process might be another 5 or 10 years. The current way NNSA is upgrading its weapons really started in 2002, and we didn't collect very good data, so it really started in 2012, and we still didn't collect very good data. Our office started in 2015. We really have reliable data from about that point onwards, with all of the holes and caveats that Abby said. So what that gives us is 2 existing programs where we get maybe the middle of development to the end of development. We have 2 ongoing programs where we're getting very early development or early development associated with it. We don't have any programs that span from beginning to end of development, much less a huge number of programs. So that's why we do a lot of work to look at individual components and the behavior of those components. But we'd love to be able to have better data that spans a long period of time, and we can't go back in time and get that, so that will only come with us continuing to collect this information. Because we're looking at the programs that have succeeded and the components that have succeeded, we do have a little bit of bias associated with the data, the things that are actually done or have actually moved on. For those early development programs, we don't know where they'll end up or how long it'll take them to reach those prior TRLs. So maybe we're underestimating. Maybe there's survivor bias or optimism bias in some of those. So the information we have is the best that's completed, not the most reliable information. And our data collection process, as Abby said, does leave itself with a lot of holes. We've implemented new policies that will make sure that going forward, we will get a much better snapshot at various points in time that will give us history and projection for components for all the programs we're looking at. But again, it'll just take time to populate that. One of the other drawbacks of what we're looking at is we are primarily looking at technology development. We're not looking at the testing programs that go into them. We're not looking at the manufacturing programs. Manufacturing readiness levels are a thing. However, they've not proven to be reliable in the NNSA. There are safety programs that are in place. None of those will necessarily drive or be driven by the TRL process. So it won't necessarily be an early indicator or even a lagging indicator of a problem. So that's why we've highlighted this as a method for early stage estimates, where we say this is the scope or risk of these type of components failing. As time goes on, we try to look at more specific design issues and say, these are the things that are causing problems and here's the impact of them. Or non-design issues. Here's the impact of the testing program being behind or not being able to have the Air Force vehicle to do the tests on, whatever else we have. So this methodology is really specific and beneficial with the early stage, but we've used it more as a cross-check as a program is advanced further where we can do better measures using traditional schedule metrics or other methodologies for schedule estimating. So I'll pass back to Abby.
So one of the goals that we're hoping to do going forward is to be able to understand the impact of the more rigorous assessments that have been implemented by defense programs. Are we seeing that components are starting at notionally less mature stages because we've said, hey, if it's not done this, you can't just, artificially put it at a higher TRL level just to get funding. And we don't know that that was happening before. So we're really interested to understand how this policy has changed how things are being assessed. We also, as Mike mentioned, there's a massive testing program associated with these weapons that by and large our insight in is fairly limited. And we really want to understand the tie between tests and TRLs, because presumably for a TRL level to progress, we know that there's some testing. Are there specific tests tied to certain TRL levels? And how does one schedule inform the other? And what sort of documentation needs to occur? Does the documentation need to occur before or after these tests occur? Additionally, we want to understand the relationship between milestones and TRL levels. In our previous chart where we showed, the phases going from development engineering to production engineering into the first production unit, we used artificial cutoffs, and we tested those artificial cutoffs to program plans and what prior programs had actually achieved. But because of the small number of programs at this point, it's difficult to test to say this is conclusively really what we're seeing happening. And, these are the TRL levels that are actually being achieved at this point. Also, we really want to understand the correlation between the types of components. So, electrical, mechanical, what if we add a nuclear component to it? Is there a different maturation timeline that occurs based off of the type of component that we're putting in there? And what is the effect if we're looking at a component versus a subassembly? Because at this currently in our analysis, we don't really have the ability to say if a lower level component that feeds into an assembly is at a lower TRL level, this will hold back that assembly, or if we have more assemblies versus, and how that works on the maturation. And so we really want to be able to understand correlations between types of components and that the parent-child relationship within assemblies. As Mike said, we're looking at this point, we've solely looked at the technology maturation side of it. We haven't really been able to explore manufacturing. Part of that's because we collected manufacturing readiness levels and we found that it wasn't providing the data that we thought it was. We had a conversation with the sites and they weren't using it how we had anticipated them using it. And so we're hoping to really be able to understand what's happening there and maybe find a better way to answer the question for senior leadership on how do we look at problems or predict manufacturing problems. We know that that there are sites that use a production technology readiness level. So instead of looking at can we produce the component, what is the maturation of the technology that produces the component look like? We know that other organizations outside the NNSA also look at system readiness levels and integration readiness levels as instead of just, individual components, how difficult is it to integrate, 100+ components into a single system work. And then we also know that there's a producibility metric. So maybe we can produce a component, but we're not producing it as regularly or at the quality that we'd expect it. And so we know that those metrics are out there. And so we really want to be able to see if we can apply the same methodology to these other readiness levels or explore a new methodology with these other readiness levels. So with that, are there any questions?
Do you anticipate keeping this study up to date, or how have you considered how you'd keep this going as you do mature more programs, and how frequently do you update it?
So we update the database yearly. So within our most recent update, we've actually started to look at the probability of a component failing as it goes through its technology maturation process. So we've looked at what percentage of components do we never see again, what percentage of components do we see a backsliding where their technology was initially assessed wrong. And we've looked at the effect of specifically electrical components. We found that that's the only subcategory that we have sufficient numbers to really examine the differences between types. And so as we extend it, we have been including that analysis, and we're hoping soon to have enough material to hopefully write a follow-on paper.
We've also matured how we can communicate the results from this. So Abby showed the bar chart of how long the program planned to do something and how long our TRL model said it would take to do that, to get to the first production unit. We've also instead looked at which are the ones that are causing the biggest problems, and doing maybe even a binary discussion. Here are the things that are on time or mostly on time. Here are the things that we think are going to be late, and here's what the program might be able to do with the ones that are on time. The ones that are going to be late, if there's no alternative technology or no way to, you can't throw money at everything, this is how long it's going to take to finish those outliers. So we're more clearly able to show and define those outliers, which I think has been a helpful discussion, especially because we're an independent entity. But when we discuss this with the program office, and they say, well, we don't really understand what kind of information, what action one could take with this information. Well, we can say, well, here's the problem if what we think is true is true. Or we can also look at how a program said they were going to do with technology maturation, where they're actually at. And that's a good way to say, this is why you're behind. You didn't mature technology on these, and here's the implications of that. And that's why you feel like you're behind, because you are.
Yeah, and when Mike talks about like that technology maturation, we're measuring it by, are you completing it as fast as you anticipated? So what components aren't being completed as fast, but also what components were just lagging behind from the get-go, and are they still lagging behind? Even if they're achieving everything else as you'd expect on the maturation scale, if they started late, they'll finish late.
Or conversely, have they caught up?
Correct.
Great points. You mentioned in their discussions with the program office or discussions with leadership, as cost estimators, it seems like it's often difficult for us to communicate with program managers, because we don't necessarily speak the same statistical based language. Program managers seem to understand schedule and TRLs, though. Can you speak a little more about, is it easier for you to discuss this methodology and its results with program managers, or is there still an inherent conflict or sort of misunderstanding of the message you're trying to convey versus what they're hearing and what their perspective of the world is?
Our program offices do not use TRLs as really stoplight charts or assessments. So I would say, in some ways, it's news to them, even though it's information they have and they have access to. It's more of a part of the process, not necessarily an indicator of status. So I'd say that part was a little challenging to get across. But I would then also say being able to, like I said, define more clearly the level of, at a level of detail, here's what we're seeing within these things. And they might say, no, that's fine. We actually know why that one's lagging. It was a paperwork issue and no action necessary. But, we really didn't understand where this one was at. And we looked at it a little bit more closely, and we think you're right. Maybe we are getting behind on that.
And we've been particularly lucky because at this point, this analysis, the only program that we've reviewed since the inception of this analysis has been with a really experienced program manager who was with us since like day one on an older program. And so we've been able to have conversations on that to understand how the program office views our analysis, and occasionally get feedback on it. And so because of it, we were able to actually build in a more rigorous policy on collecting TRLs that will allow us far more information for future programs.
Thanks for the response and for your thoughts.
Thank you, too. Thanks for the questions.
Any other questions for the team here? Okay, I'm going to go ahead and share in my screen. Thank you very much. This is an excellent presentation. Appreciate it.
Thanks, everyone.
Thank you.
Okay, so everyone, please fill out the survey. I also dropped a survey. You can either scan this barcode, this QR code right here, or you can go to the chat, and I've dropped in the link there for the survey as well. And the results from these surveys help us to better shape our future events and to determine the winner of our Luncheon Speaker Presentation Excellence Award. So please participate and give us your feedback. Leave that on there for a second. All right. Also wanted to encourage those of you who have not become a member of ICEAA to please join. That we have many benefits of ICEAA membership, included discounted registration to the annual professional development and training workshop. This last one we had in Pittsburgh, and the next one is in San Antonio. We have many local and regional seminars, a subscription to the ICEAA World magazine, and eligibility to submit articles and papers for publication in ICEAA World, and of course to the training workshop, and discounted pricing for CBOC and access to the Cost Estimating Career Center. Membership rates, these are current membership rates. They just switched over, but 1 year membership is $150. There's about 10% discount for 2 years and more for multiple years. Please check with your company or organization. Often they will reimburse you for membership fees. And I'm going to turn this over to Dan, a little recap.
Hey, thanks, George. Let's see, I should be coming through here. Thanks everybody for joining today, and thanks to our speakers for that great presentation. Always interesting to see new and novel techniques. I also wanted to thank everybody that came out to our all members meeting last week. We've got like this, the slide there on the left, and we've got some pictures here on the right. It was great hearing from Mr. Loftus from DASA CE. We got some great presentation and update on national from Megan Jones. We can see here that there were free drinks and food. The photographer of this obviously ran out of drinks mid-presentation there, but still good to highlight and good that we got some libations along with that free food. Here's George giving us a great update during the chapter board review. And here's Courtney and I giving out some chapter awards, and here are the happy award winners. So if you didn't get a chance to make it to the all members meeting, note that we will be having additional in-person meetings coming up here in the not too distant future. We hope that you all can make it to those and do some networking and enjoy some time with the chapter. George, I think this one's mine too. We are hoping to have some more luncheons this calendar year, and we do shoot for them monthly. We might take a month off in December, or maybe just do a quick get together since a lot of folks will be busy with the holidays. But do please let George or myself know if you've got a topic that you want to talk about, if you want to present to the chapter. We're always looking for new presenters to talk about new and novel techniques and things that they've come up with. So the contact information is there on the screen. And thanks everybody for joining today. I hope you enjoyed it as much as I did, and you learned something as well. Thanks.